In this video, we will be providing an end-to-end explanation of the question Kate smallest of two sorted arrays. Let's discuss the problem statement. We are given two integer arrays sorted in ascending order, A and B, along with a valid integer k. We then would like to find the Kate smallest element within the union of both arrays. As an example, if A is the list 1, 5, 10, and B is the list 2, 3, 4, 8, and k is 2, then the answer is 2, as shown. A naive approach consists of allocating two pointers, one for each array, and starting from the beginning, we will iterate k times to find the answer. This approach takes O of k time. The drawback of this approach is that when k is large, the algorithm may perform slowly. To obtain a logarithmic approach, we observe the following insight. If both arrays are partitioned into smaller and larger halves and the maximum of the smaller halves is less than the minimum of the larger halves, and the sizes of the smaller halves sum to k, our answer is the maximum of the smaller halves. Taking the first example, we have that the smaller half of A is less than the larger half of B and vice versa. And so the answer is then the maximum of the smaller halves, which in this case is 2. So the fourth smallest of A and B in this case is 2. For the second example, we see that smaller of B contains 4, which is greater than 3, which is located in larger of A. Therefore, this selected partition does not meet our requirements and we need to find a new partition. For reference, denote our desired property of the smaller halves as star, as annotated in the first example. Recall that we want two smaller halves such that they have a combined total of k elements. It is important to note that once we have selected a choice of partitioning index for A, our choice of partitioning index for B is fixed, as shown in the equation k minus I sub A. If we observe the possible situations that can arise, there are three possibilities. 1. The maximum of the smaller half of B is greater than the minimum of the larger half of A, in which case we increase the partitioning index of A. 2. The maximum of the smaller half of A is greater than the minimum of the larger half of B, in which case we decrease the partitioning index of A. Or 3. Property star is satisfied, in which case we return the desired value. This sort of logic is identical to binary search. Let's go over the pseudocode for an algorithm. We start by initializing our lower and upper bounds for binary search. Then we compute the mean index which will be used to partition array A. Then we compute the partitioning index of B using the formula. Lastly, we implement the logic from the previous slide regarding how to proceed under the various conditions. If we have not returned a solution within the loop, we return an error. The key edge cases of this algorithm have to do with when we encounter invalid indices. This may occur, for example, when all the elements in one array are strictly greater than all the elements in the other. If a lower index is invalid, we assign -infinity to the target value. If an upper index is invalid, we assign +infinity to the target value. A key edge case is that if the partitioning index of A is greater than k, we must decrease the partitioning index of A. Also, if the length of B is less than k-1, we must increase the partitioning index of A. The median of two sorted arrays problem reduces to an instance of the Kate smallest of two sorted arrays problem. The key logic is that we consider the case when the total number of elements are either odd or even, and in the respective cases, we return the appropriate value. If you found this content useful, you should consider algorithmspath.com. You can use the promo code SupportVectorMachine for a discount. Thanks for watching.